All right, so the other day we started with example 1, and you were given the following cubic function. We previously found the velocity, and I'm going backwards kind of for Corey. So the velocity is v of t equals 6t squared minus 6t minus 12, and my units are meters per second. The acceleration is the derivative of velocity, so it's 12t minus 6. And then as you go on, your seconds increases. So position is meters, velocity is meters per second, acceleration is meters per second squared. So the acceleration is 12t minus 6. And then in the next part, it says find the acceleration after 1 second. So that's like A, it's from the other day. That's A of 1. It's right after the velocity graph. And then it says find the acceleration at the instance when velocity is 0. So we had picked up and we said, okay, v of t equals 0 when 0 equals 6t squared minus 6t minus 12, which was when 0 equaled t squared minus t minus 2. And we got our times as 2 and negative 1. But if you go back to the initial condition, the time cannot be negative because in real life, time can't be negative. So t of negative 1 did not matter. So to find the acceleration at the instance when velocity is 0, we are finding t of 2. So a of 2 was equal to 12 times 2 minus 6, or 18 meters per second squared. So as we progress, we talk about the position and velocity of particles, and we talk about their displacement. So the displacement has to do with final and initial. So the displacement of a particle during the first 2 seconds, we care about its initial position, which is at s of 0, and we care about its final position, which is s of 2. So s of 0 is 3. S of 2 is negative 2 squared is 4. All right. I thought I maybe missed a value for a second. Is negative 1. So our displacement is final minus initial, or negative 1 minus 3, which is negative 4. So what that means is that after 2 seconds, the particle is 4 units to the left of its initial position. It doesn't mean it only went 4 units. It's just after 2 seconds, it's 4 units to the left of where it started. Find the velocity at time t. So that's finding the derivative. So s prime of t is equal to the velocity at t, which is equal to the derivative of position, which is 2t minus 4. And again, t is measured in seconds and s is in meters. So my units are meters per second. And then the next question is, what is the velocity after 3 seconds? What is the velocity after 4 seconds? So what we're going to do is find v of 3 and v of 4. So you get 6 minus 4, which is 2, and 8 minus 4, which is 4. So the velocity is positive at both of those units. So what that means is that if velocity is positive, we are moving in the positive direction or moving forward. Find the acceleration. So a of t is like finding the second derivative of position, or simply finding the derivative of velocity. And in this case, it is 2 meters per second squared. Therefore, the acceleration at any time will always be 2. So if they ask you for the acceleration at 4, it's 2. The acceleration at 10, it's 2. So on and so forth. So now the physics starts to come into play in calc. It says, when is the particle at rest? A particle is at rest when our velocity equals 0. So the particle is at rest when velocity is 0. So in the case of this problem, 0 equals 2t minus 4. So therefore, at t equals 2 seconds. Yeah, that's just a coincidence. Then, in the next part, it's when does the particle move to the left? When does the particle move to the right? So a particle changes direction when it's at rest. A particle can only change direction if a particle is at rest, right?
Maya Mahoney, please report to the office. Maya Mahoney.
It's supposed to be 2. What's your grade in Maya? -10.
All right. A particle will move to the left when velocity is negative. A particle will move to the left when velocity is less than 0 or negative. Therefore, a position of a function is going to the right when the velocity is positive. So what we want to do is kind of look at a graph and compare the velocity of the function. So the velocity from 0 to 2 means I need to investigate v of 1. So
since we already did velocity something before to it, like after to it.
Yep, and what was it? Exactly. So at 3 and 4, yes, because a particle does not always have to change direction just because it goes to rest.
Oh, so when it goes to rest, it can change direction, but it doesn't have to.
Exactly. So like an example of that would be like a function that maybe goes like this. So like it might come up, hit 0, and then go back down, and then come back up again. So here, if this represented velocity, it would equal 0 at point B and point A, but the velocity stays negative. So like here's your A, here's your B. The velocity is negative, velocity is negative, then it's positive. So it's moving left from negative infinity to A to B, and then right, B to infinity. But it, no, because in A it's not moving left or right, it's stopped.
So particle can only change direction. Can only change at when it's in rest, but it doesn't have to.
Correct. So it'd be like, even if you just take into account yourself walking, like you could walk, stop walking, go forward again, stop, and then go back up. Okay. So in the case of this problem, at 3 and 4, we know it's positive. At 1, 2 times 1 is 2. 2 minus 4 is negative. So at 1, it's negative. So for this problem, the particle is moving left from 0 to 2 and right from 2 to infinity. If it had an end, like if it said, when does the particle move left or right over the first 10 seconds, then it would be 2 to 10, and the 10 would have a bracket. Okay. And then the next is find the total distance traveled by the particle during the first 5 seconds. And this is actually what I started to do on your homework. Instead of displacement, I jumped to total distance. When you were having issues with it, I wasn't paying attention to the wording very well. Total distance is the absolute position with particle changing direction taken into account. So since from 0 to 2, the particle is going backwards, and then from 2 to 5, the particle is moving forwards. To find the total distance traveled, we need to find the distance traveled from S of 5 to S of 2 and add to it the absolute value of the distance traveled from 2 to 0. Sorry. You can make S and X. That's the other variable that you'll see for position is X, because it's talking about movement along the X axis. So they'll talk about like X of T. Okay, so S of 5 is 25 plus 3, which is 28, minus 20, so 8. And then S of 2 is 4 plus 7, which is, or 4 plus 3, which is 7, minus 8. So you get negative 1. To the original. So we get 8 plus 1, which is 9, negative 1 minus 3, which is 4. So the total distance traveled is 13 meters. Even though at 5 seconds, the particle is at 8. And our displacement would be S of 5 minus S of 0, which would be 8 minus 3. So the displacement is 5 meters. The total distance is 13. And the position is 8. Does that make sense? Can we see like all of the differences? Correct. 8's the position at 5 seconds. The displacement from initial to final is 5 meters, but total distance traveled is 13. And then I told you today we would talk about speeding up and slowing down. So a particle is speeding up if velocity and acceleration have the same sign. A particle is speeding up if velocity and acceleration have the same sign. So what that means is that the velocity is negative and the acceleration is negative, or velocity is positive and acceleration is positive. So they're either both positive or both negative. A particle is slowing down when velocity and acceleration have opposite sides. So meaning V of t is negative and A of t is positive, or V of t is positive and A of t is negative. Is everybody okay with those definitions? So if you think about this problem in particular, we have that velocity from 0 to 2 is negative, and from 2 to infinity is positive, the acceleration is always what? Yeah, because our acceleration in the case of this problem is always a constant, like a of t equals 2. So the acceleration is always positive. So what we do is create a comparison of their signs. So from 0 to 2, are the signs the same or different? Different. So the signs of acceleration and velocity are different from 0 to 2. Therefore, it is slowing down from 0 to 2. From 2 to infinity, both velocity and acceleration are positive. So if velocity and acceleration are positive, then the function is speeding up.
So it's going to continue to speed up.
Correct. Let's graph these functions. So in order to graph them, I'm actually going to give you guys well, in this case, we have all our functions, right? And then we'll talk about graphing it without having all of the functions. But let's talk about acceleration because it's the easiest. Acceleration equals 2. So it's a horizontal line at 2. Velocity isn't too terrible. It's 2t minus 4. So you start at your y-intercept. And then we go up 2 and over 1. And hopefully on the graph, you can see how at 2 seconds, velocity is a 0. And again, when it comes to speeding up and slowing down, you can see from the graph where they're in different quadrants. And then last but not least, we will graph position. And if you think about it, we said that the initial position is at 3. So here's S of 0. We calculated that. We also calculated S of 2. And at S of 2, the height of the function was at -1. And then we also found S of 5 and said it was 8. Sorry. But the idea is there, right? You would also be able to, if you could figure out it was a quadratic, if 0's at 3, then S of 4 is also at 3. Because this is down and over the same equidistance, and a quadratic is symmetric. And the vertex of the quadratic will be the 0 of the velocity, because it would create that horizontal tangent right there where the slope is 0. So again, you could do symmetry based off of the vertex of the quadratic, which now if you put into play, which is why we did the quadratic warm-up, the vertex of the quadratic is when its derivative is 0. The vertex of the quadratic is when its derivative is equal to 0. Not a coincidence. All extremas will have derivatives of 0. All extremas have derivatives of 0. Correct. Green is position, velocity is blue, and acceleration's red. So honestly, all we're doing is extending our ideas, concepts, and knowledges about position, velocity, and acceleration today. And the discovery of calculus was concerned with velocity and acceleration. So physics and calc really are interrelated bodies in the fact that both began with the study of free fall, interpreting force and gravity, because our early scientists such as Aristotle, Galileo, and Newton really wanted to understand why objects fell in the way that they fell. So the idea is that if we lived in a world where there was no gravity, a leaf and a bowling ball would fall at the same rate. But we don't live in a gravity-less world, so gravity affects the weight with which objects fall and gives us our 9.8 meters per second, because that is the pull of an object. So if a ball is given a push so that it has an initial velocity of 5 meters per second. So again, if you push an object, you are an outside force acting on it, thus creating that initial velocity. So we give a ball a push, its initial velocity becomes 5 meters per second. It's going down an inclined plane, and its distance is given by the function s of t equals 5t plus 3t squared. Find the velocity after 4 seconds. So velocity is the derivative of position. So 5 plus 6t. Velocity after 2 seconds is the instantaneous velocity, which is v of 2. The little curves on them. Yeah. And then part B, how long does it take for the velocity to reach 35 meters per second? So we have different things, right? So this time, the velocity at 2 seconds is 17 meters per second. So if I want to know a time, then what I'm going to do is kind of set the function equal to 35 meters per second. and work backwards for time. So what that means is that I am going to set velocity equal to 35 and solve for t. So it takes 5 seconds for the velocity to reach 35 meters per second. It takes 5 seconds for the velocity to reach 35 meters per second. I feel like this is the most used example of vertical motion. So it says a dynamite blasts a heavy rock straight up with a launch velocity of 160 feet per second, which is about 109 miles per hour. It reaches the height of the following, and then we want to answer. So again, here's my little rock on the ground. It's getting launched straight up. Yes. No. And comes straight back down. Yeah, this was in feet per second. So it says, how high does the rock go? So the max height of the rock your packet's up on that paper, on that table. No. But I was just starting a new example, so I'll wait for you to get in your packet to example 2. So how high does the rock go? The rock goes to a max height when velocity is 0. So we need to know when is v of t equal to 0. In order to know that, we actually need our v of t function. So that's 160 minus 32t. So we want to know when 160 minus 32t equals 0. What? So it's 5. The velocity will be 0 at 5, or the rock will reach its max height at 5 seconds. That t of 5 is not our answer. It says, how high does the rock go? So you have to take 5 and plug it back into height. Yes.
On that homework, before I realized that when velocity is max height, I was just doing the negative v over 2a. Let's say on the test I forgot, could I do that, or do I have to set velocity equal to 0?
It would work if and only if the initial function is a quadratic.
Okay.
So like the one example we did today was a cubic. So then it wouldn't work. But yes. Okay. So we get 400 feet. The position at 5 seconds, or the height, is 400 feet. That is the max height of the rock. That is the max height of the rock. What is the velocity and speed of the rock at 256 feet above the ground on the way up, on the way down. So it would hit 256 feet twice because it has to cross it once to go up, then once to go down. So you would set the position function equal to 256, work backwards. So we would set that equal to 0. So that's like negative 16t squared plus 160t minus 256. And exactly, you can take out a 16. Something similar.
Then I pulled out the negative 16, and I got t squared minus 10 plus 256 and 82. No, it's number 3 of the 1 through 10.
Yes.
All right, there's my 8 from you. Jump 3 steps ahead on us.
So these represent the x-intercepts, technically, of the quadratic, which represent the 2 times at which it reaches this height. And then it says, what is the velocity and speed at this height? So the velocity at 2, the velocity at 8 versus the speed at 2 and the speed at 8. When are the velocity and speed going to be different? Well, exactly. When it's falling down, exactly. So the speed and the velocity are the same at 2 seconds. The speed at 2 and the speed at 8 are both 96 feet per second because speed is the absolute value of velocity. I plugged 2 back into velocity. So velocity is the derivative of position, which was that 160 minus 32 times t. Correct. And then it says, what is the acceleration of the rock at any time t during its flight after the blast? Good? Perfect. So derivative of velocity gives acceleration. So the derivative of 160 is 0. Derivative of negative 32t is negative 32. So what that means is that the acceleration is always downward. So if you go back to our concept of that speeding up versus slowing down, we know that the velocity is 0 at 5 seconds. So from 0 to 5, would the object be speeding up or slowing down? Because again, you know for v of t, 5 seconds is where it changes. At v of 2, it was positive, and at 8, it was negative. And acceleration is always negative. So from 0 to 5, they're opposite signs. Therefore, it is, and then from 5 to infinity, well, not really infinity, it would be 5 to when it hits the ground. So when would the object hit the ground? Perfect. So let's jump to D real quick. So when 0 equals 160t minus 16t squared, which I probably was jumping, no, I didn't jump ahead with my speeding up and slowing down, it's just not on there. So when does this equal 0? Good. And if you think about the object, if it takes 5 seconds to reach its max height, that's halfway up. That means it's going to hit the ground 5 seconds later.
There's one on the homework like that. Do I need to show when it asks, like, because it says something about when it reaches half the max height or when it reaches the ground? Can I just show my flat short?
You'd show the quadratic stuff, and then you could do it. You could use your, that's what she asked. You use your quadratic ideas. If it's a quadratic. It only works if it's a quadratic. Like the one I drew over there on the board wouldn't work. So that's why we start with quadratics and start with understanding it. And then our position and velocity and acceleration functions are eventually going to become quartics, cubics, etc. So we're starting easy.
Did you
So the rock will hit the ground when its height is 0. So what we did was take the height of the rock and set it equal to 0. And you get 2 values because this is its initial, it starts on the ground. And then this is when it hits the ground again. An object that would be, and that's what I was saying, like our quadratics are going to get more complicated. Sometimes you're told objects are launched off of a building. So the initial height versus the height when it hits the ground are not the same anymore. So right now we're starting with very nice, like prim and proper, easy quadratics to understand the concepts of velocity and rates of change. As time progresses, these concepts are going to become more challenging and more conceptual. So again, the other day we talked about engineers, economists, doctors, all using calculus. The last thing we're going to talk about today is in the economy world, how do derivatives relate to money. So if you took econ at any point in time, you might have heard of marginal cost or marginal revenue. The word marginal in calculus is a fancy way of saying derivative. The word marginal in calculus is a fancy way of saying the derivative. And that's what this says right here. So in example 3, it says, suppose you have the given cost. You want to talk about when it produces 8 to 10 radiators. R represents revenue. So it says find the marginal cost. So that means to find the derivative of the cost function. Find the marginal revenue. So that's the derivative of the revenue function. So you have marginal cost and marginal revenue. We are currently producing 10 radiators a day. So we want to look at C prime of 10 and R prime of 10. And in order for a company to be making money, what am I hoping for? Yeah, a positive in the cost versus the revenue. So the cost would be 3, 10 squared is 100. So you get 300 plus 12, which is 312, minus, oopsies, that should be a 12 times 10. Minus 120. Go ahead. Yeah, I totally started to write the wrong. Thank you. I like mixed revenue and cost. Actually, I found revenue. Sorry. So if your rate of change of cost is 195, your rate of change for revenue is 252. Is your marginal revenue greater than your marginal cost? So my marginal revenue is greater than my marginal cost. Therefore, I have a profit and I am happy. All right.
Yes. Yes. 4 problems. Actually, they just the most recent episode. I want to see Jeffrey. I don't like him. Yeah, I'm surprised the last one all that he has. I know, he just looks like a little fat rat. I don't mind him. I I don't like the most very much. I don't either. But she's so uninterested in them. Like they're talking, like they tell something like she goes, okay, next. Well, she's an actor. She's gonna be fake.
All right. And then 37, use a calculator. I want to try it because it's a calculator problem. So two of them you got passes for me, didn't you? Yeah, if you want, you can start telling them you're going to be in here permanently.
Well, I told him that, but I didn't tell him.
You have to tell Miss Ashmore, yeah. All right, look, your math homework isn't terrible.